My name is Ming Lu. I work in the Wolfram Alpha scientific content team. So normally I work on Wolfram Alpha, but today I'd like to present a paclet I worked on called Convert Archive Text Source. The camel case phrase in the title is both the name of the paclet and the single user-facing top-level function in the paclet. The purpose of this paclet is to provide functionality and a framework to convert equations in archive preprints from TeX to Wolfram Language using large language models, in particular the AI API. So I have this paclet and function published as resources in the Wolfram Cloud, and I have example outputs and inputs in the cloud under my page. And the task or experiment setup is very well defined. Archive is the open archive of about 2 million research papers. It provides both the text source files and the human readable PDFs. And TeX is the standard language for typesetting scientific content, in particular mathematical formulae. So the specific task or experiment I'm doing is for a given paper, I will take the text source file. It can be the entire file or a specified range of sections from it. Then I extract the equation-like objects from it. With both, I construct a prompt, typically a very long one, together with a set of instructions to convert the equations from TeX to Wolfram Language input expressions. Then I send that as a long prompt string to OpenAI API. After a while, I got the result, which is also a long string. Then I parse that into a structured Wolfram Language expression. Then I either return the result, the converted equations in Wolfram Language, along with some auxiliary data as a data set or as a well-formatted Wolfram notebook. So why this is useful or interesting? TeX is the industrial standard for typesetting, but it's strictly for typesetting. The equations represented in TeX is not computable and has limited interactivity, by which I mean you cannot easily and quickly change something or add a term in math formula and quickly reevaluate some function involving that function to see the difference, or you cannot plug it in a plotting function to see the visual aspect of it. So that need of having a computable version of these equations is always there in the right contexts. So with the advent of large language models, it opens up a lot of possibilities. They can be used as text translation or processing tool. They can be used as code generation or conversion tool. So in my context, I have large amount of TeX source files as I treat them as textual data. So it's relevant for text processing purpose. And the output, one kind of output is the auto-generated executable or close to executable Wolfram Language input commands. So it's relevant for code generation. And if you imagine making a human programmer to do this conversion, it can be difficult, if not infeasible, because of too much work and too little expertise. Because you need to understand to some extent the subject matter in the research paper in order to do the conversion, do the programming work. Then you also need to know sometimes some advanced feature of the Wolfram language in order to do the advanced level programming. So it's advanced because the content of these equations may be require some obscure knowledge of the language. And use cases the output can be saved in notebooks, and such notebooks can be used as a starting point for programming, making programs about the content in the paper, or it can be used as a reference. If the output is a data set, you could also use it for further analysis as a starting point, possibly with some curation first. Well, I will quickly show you some example input and output. The input is just the text source file for a given paper, and text source file typically look like these, and it's for typesetting. And I will extract the equation like objects from it. So in this particular example, it'll be the things like these and these. So they are the equations that sandwich between a pair of begin equation and end equation. So I use both the whole paper and the extracted listed of equations as ingredients for creating my prompt. So the output is a notebook like this. So it's a well-formatted notebook. Each equation is represented by one entry like this, and each entry has multiple cells with color coding. So the first cell is the original the copy of the original TeX code for that equation. And the second one is a rendered version of that. So this is generated by import string. On that string with the second argument TeX. And it's sometimes it doesn't work. If it doesn't work, it just says not available. Then the last three cells for each entry is generated by LLM. And the main output is the last one, the last cell, which is the input command that corresponds to that TeX expression, TeX version of the equation. So this is something similar to what you would enter in a normal input cell and to evaluate. And the second last cell is the same thing, but in traditional form. So it's closer to the formatted TeX. The reason to put here is it's auxiliary. Sometimes it help you to compare the two to tell if it's correct or close to the original. And for each equation, during the generation, I also ask LLM to make a comment about the conversion. So I explained when the output is a notebook, what does the output look like and what each cell is. Then I want to explain the usage of the function. So for this, I will use the function source documentation, and I will use a local version. So it's the function source, the function resource documentation page has a nicely formatted usage declaration, different calling signatures, and some explanations about the options, and also examples of typical usage. So there's really only one top-level user-facing function, which is by the same name as the paclet. And the first argument is the ID of the archive paper, which uniquely identify a paper. Then the second argument is the range of the specification of the portion of the paper that you want to apply this conversion. And it can take several different formats. So I usually work with sections. So you can take one section. So the IDX will be the index of the section, first, second, third section. Or it can be the starting and the ending index of a range of sections. Or you can specify all the sections. So this will be effectively the entire paper. I do make some pre-processing of the text source file. For example, the bibliography section is usually dropped because typically there's no equations in it. And for example, I delete empty lines. Yeah, I do these pre-processing. So, but the way to specify the range of the text source to do the conversion is through the second argument. Then the third argument is called prompt recipe. What that means is it's a named combination of pre-made prompts. So it's a sequence in a particular order. It's a sequence of pre-made prompts in a particular order for a particular purpose. And currently there's only one named recipe, which is equation list. So equation list is targeted for this specific need, which is converting equations in this paper from TeX to Wolfram language expressions. And by expression, I mean the input commands that you normally would use in input cells. So the reason I make it as an argument is in principle, there's room to make multiple different recipes. So you could imagine, given a paper, given the text source of the paper, you could do different things. And they will require different prompt recipes, and you can pre-make them. So they will have different names. So that's why there is a third argument. Then the fourth argument is format, which specifies the output format. It can be dataset, notebook, or cloud notebook. So a dataset means it will return a computable dataset. So you can do data analysis with that. It can be notebook, which is the notebook I just showed you. So that's if you want to actually read these as a reference, or it can be used as a starting point for making programs. So you can copy these out or directly modifying these. Cloud notebook it means the notebook is going to be published in the cloud, and it uses $cloud base to specify which cloud you deploy it to. So after it's deployed to the cloud, it looks like this. So pretty much identical to the local cloud, to the local notebook. Yeah, I think because it's very large, it loads slowly. Okay, then I will discuss some useful, interesting options. So this functionality, this paclet requires OpenAI access. So you need to have an account on OpenAI, and it has to be the kind that has access to API. So you will need to generate an API key, then set the system credential to your key before running any of these commands. That's one important thing. And then the other one is, so we have a very long prompt, and it sends that to OpenAI API. OpenAI API calls can be slow, especially with a long prompt. So I have an option that can turn on multiple parallel kernel to run that slow large language model API call. It actually runs multiple API calls. Then it'll automatically partition the input list of equations into smaller chunks, smaller sublists, do the API call, then receive the results, then join the results to return before returning as the final result. So that's controlled by this option. So another useful option is this. So you can, besides the built-in prompts that's hidden in this named prompt recipe, you can provide additional prompts with this option. So each PI must be a string, must be a prompt string. And all of these will be joined together and appended at the end of the built-in prompt. So the built-in prompt depends on the paper. It contains the paper, right? So that's constructed on the fly. So I will just explain these. Then I will show some typical usage examples. So you call the function with one paper, then you specify section 3, and then a named prompt recipe, then dataset. So it'll extract the equations from section 3, then turn them from TeX to Wolfram Language, then return the result along with auxiliary data properties in the dataset. So this is the title of the section. This is the labels of the equations, and this is the original text source of the equations. And this is the converted Wolfram Language code. And this is the comment the large language model made on the conversion. So instead of dataset, you can also let it return as a notebook. So the notebook looks like the one I just showed you. You can also, by default, it saves in the $temporary directory. So that won't survive rebooting computer, I think. You can also specify option save file queue and the option root directory. So the result will be saved in a directory you specify, and that will be persistent. So it'll, in this case, I generated the output for section 2 of this particular paper in a notebook that's saved in this file path. You can also publish it in cloud. So if you specify output as cloud notebook, and you use this option to publish it. Yeah, so that's the usage. Then I will explain a little bit of the inner workflow. So if you think about it conceptually, it is actually quite simple. I will fetch the text source file from archive server for the given paper, then save it in the symbol S1. Then I will collect the equations from that, then save it in a symbol S2. Then, along with a set of instructive prompts, P1, P2, etc., I will, on the fly, construct a long prompt, so symbolically represented as capital P of P1, P2, S1, PI, S2. Right? In terms of actual code, it looks something like this. Right? So most of these are constant prompts, so they are strings, constant strings. But 2 of these are dependent on the input paper. So they actually contain either the whole paper or part of the paper or the list of equations extracted. So all of these are, when it's evaluated with a real paper, it'll be many different strings. Then they are fed into LLM synthesize the built-in symbol to form a large prompt and sent as a API call to OpenAI. So so I will skip these more detailed things. So I will show you a example API call, the prompt. Prompt. So this is a one example prompt. It's very, very large because it has to contain the paper and the long list of equations, right? So I can scroll down all the way to the bottom. It's a very long string. So that thing is sent to API, OpenAI API. Then after it gets results, I will parse the long string result, mostly using regular expressions. Then that turns into a structured Wolfram language expression, essentially a data set. Then I can optionally format that and save that as a notebook, the one you just saw. So I will quickly discuss a few points about the implementation. One is about the context lens. So it's recommended to use the model GPT-4 Turbo. It's also the default value for the option LLM model. It allows a total context length of 128K tokens. So that's the total tokens allowed to accommodate both the input and output. So recall my prompt actually contains the long string of the paper and the list of equations. That's why we need this model, which has a long context length. The output limit is 4K tokens, right? So that accommodates on average about 10 equations. So that means each API call can return you about 10 equations. That's another reason why parallelization is important. You don't want to wait, each time you get 10 equations, but if you have more equations, you need to partition the input into sublists, then ideally parallelly process them. So I used other models starting from 3.5. It performed pretty poorly. Then for GPT-4, it allowed 8K tokens, which isn't working well for my need. Then GPT-4 32K actually never really worked. And the more recent 4.0 mini and 4.0, 4.0 allows 16K for output, and it's optimized for long and complex reasoning. But in my experiment setup, I didn't observe significant improvement. So GPT-4.0 mini, I have limited experience. I also didn't observe a significant difference. Prompt length, right? So the prompt, my very long prompt, it's dominated in terms of length, it's dominated by S1, which is the paper or the portion of the paper. So the typical overall prompt length is 10 to the 5th number characters, or 10 to the 4 tokens. And to estimate the token length, there is actually an internal function. So I need to do that in order to correctly or in order to partition the input list of equations into small enough sublists so it can fit into my context limit, but also maximally use it. And I have to use parallelized API calls because first it'll accommodate my long list of equations. Second, it'll save time. So timing. When I parallelize my OpenAI API call by 3 cores, it's typically a few minutes per paper. And so this is tested on a sample of about 100 paper. And if this is super long paper, for example, this particular has about 100 pages and about 500 equations. So it's almost like a book. That with parallelization, it took about 7 minutes on my MacBook Pro with this option. So the average speed, so a few minutes for a paper, a few seconds for an equation on average. Robustness, so I use the syntax queue to validate the converted input expression. And that on this sample, it has 80% syntax queue true. And my gut feeling, so this is somewhat anecdotal. It felt like about a third is good, looks good. About a half, more than half, looks useful enough, and maybe less than 1/10 looks very bad. Looks just bad failures. So yeah, so maybe yeah, that's pretty much it. Yeah, so in principle, this could be extended, right? So I currently my instruction, my constant prompts, which is about instructions about the conversion, specifically says things about TeX to Wolfram language conversion, but the overall framework, the overall design could work for some other X to Y conversion. I just want to mention that. Yeah, that's pretty much it. Hi, yeah, so there are some questions in the chat window. Actually, in terms of model, GPT-4o should also be pretty good. The default currently is GPT-4 Turbo, but GPT-4o should be cheaper and faster. Yeah, so there are some hidden options that's not exposed on the published paclet resource page. For example, the list of tags for for identifying what are considered, what are counted as equation-like objects. In future versions, I can expose that option. So right now it includes equation array, double dollar signs, and a few other similar ones. Okay, if no more questions, that's the end of my talk.